So we're now going to talk about the backpressure models that Project Reactor's Flux class provides. And I'll talk here about first why we need to have backpressure in reactive systems. I'm then going to talk about how there's a method on a subscription called request that allows backpressure aware publishers and subscribers to bound the amount of data that's sent between them. And then we're also going to talk about something called overflow strategies that allow backpressure unaware publishers and subscribers to utilize the resources appropriately given the task at hand. Let's first start by talking about why we need backpressure. So classic client-server systems don't need backpressure since the two-way synchronous request-response interactions used by classic request-response two-way calls provide a limited form of flow control. So you make a call, the caller blocks, the callee does its thing, sends back a response. Then the caller makes another call, the caller blocks, the callee does its thing, sends back a response, and so on and so forth. So there's really no need to worry about sending too many requests because you're doing this in sort of a lockstep request response style manner. However, for reactive streams where publishers can produce events faster than subscribers can consume them, we need some form of backpressure. So here's an example where we have a publisher that's publishing 10,000 events per second, and for whatever reason, the subscriber can only process 7,500 events per second, and therefore, at some point, it's going to get overwhelmed, and if we don't have backpressure, trouble is going to occur. So let's talk about how you can apply backpressure in various ways and at various points in time and various locations throughout a reactive system. So as you can see here, we've got one way of doing it by controlling the rate or the amount of data the publisher sends in the first place. So if we can limit the publisher to sending only 7,500 events per second, which is the rate the subscriber needs, then the subscriber ought to be able to keep up. Now, this is good in theory, but it's not always practical, especially in cyber-physical systems where sensors emit data when sensors emit data, and you may or may not be able to slow down the rate at which they emit data. Another way to do things is for the subscriber to store the events temporarily until it can process it. And this works nicely when you have bursts of input, where you don't have too many events per second all the time, but every once in a while you might have 10,000 events per second, but then just for a short time. So in that case, the subscriber can buffer them and then it can play it out as time goes on. The downside, of course, is if you're not careful and this goes on too long, you'll eventually run out of memory in the subscriber because it can't buffer things indefinitely. In that type of a model, then you may want to do a dropping approach where you discard events that can't be processed immediately. So this is what happens when you're getting overwhelmed. This is the Lucy and the Chocolate Factory model where you just start dropping stuff because you can't keep up with the rate and you can't buffer it all. Now, this is not a bad model if data coming next is going to be just as good as the data that you dropped. But if the data or the events have value, if it's like a stock trade or something that's really important, then you probably can't get away with that particular model. So let's talk about the backpressure approaches that Project Reactor supports via its Flux class. So there's several types of backpressure that it supports. The first are so-called backpressure-aware subscribers that can inform backpressure-aware publishers how much data they can consume. And this is what we looked at before, where the subscriber indicates how many events it can take. Notice that this is not done on the basis of rate. It's done on the basis of how many chunks or how many elements can be sent without having to wait for the next chunk. The goal, of course, is to avoid overwhelming the memory and processing resources on the subscriber if the publishers generate events too fast. So we want to flow control the publishers so they don't generate events faster than subscribers can consume them. This, of course, requires publishers and subscribers to interact and collaborate. So in particular, the on-subscribe method in a subscriber is passed a subscription, and then the subscriber can use that subscription to indicate to the publisher how many requests it can take before it needs to request the next batch. And if you give a value that's the max value, then that's assigned to the publisher to just blast away as quickly as it can. Otherwise, if you get something less than the max, the publisher will send that many and then wait for the subscriber to ask for the next chunk. Non-back pressure aware subscribers, those are ones that don't use the subscription approach we just looked at, can apply an overflow strategy if they can't keep up with fast publishers. And we'll talk more about this shortly, but there's basically 5 different types of strategies. There's a buffering strategy, a dropping strategy that drops the latest value. There's an error strategy that throws an exception. There's one strategy that's kind of weird called ignore that we'll talk about. And then there's another dropping strategy that will drop everything except the latest value. And we'll talk more about that. And this mechanism is useful if you have publishers that don't want to be flow controlled. They're just going to be like Sonic the Hedgehog and blast away as fast as they can. And this gives a way for the subscribers to not get overwhelmed through one of the means we just took a look at. And we'll take a closer look in the next part of the lesson. So that's the end of the overview of back pressure models in the Project Reactor Flux class.